The next type of hydrocarbons are called alkenes. We know that alkenes are having a general formula of CnH2n. They are the first of the types of the unsaturated hydrocarbons we have. So we define alkenes as those hydrocarbons which contains at least one single double bond. At least one double bond. So that's the most important thing about the alkenes. CnH2n is their general formula. Now what we need to know is their structure first. The structure of alkenes. The carbon which gets double bonded are always sp2 hybridized, remember. So their electronegativity is higher than what the carbons in comparison to the carbon which are sp3 hybridized. Moreover, the double bond, due to this double bond, this bond length is 134 angstroms unit, and it's less than 154 angstroms unit, which we have in case of carbon-carbon single bond in case of ethane molecule. So this is smaller. Plus what we find is the bond enthalpy is much higher. The bond enthalpy of the ethene molecule is approximately 681 kilojoule per mole, which is quite higher in comparison to about, this is about CC double bond I'm talking about. Bond enthalpy we know of the C single bond is approximately 348 kilojoules per mole. So this shows that they are very stable in the sense of their bond enthalpies. Another important thing about this is that since these two carbons are sharing their 1 electron in the form of the pi bond, what happens is the electron density is very high. And as a result what we find is, due to this high electron density, what happens is electrophiles of the species which attacks on this. That's why they show electrophilic addition reactions. Now let us see their nomenclature. We know that we call them alkenes, and we need to put the locant or the position on which the of the carbon atom on which the double bond exists. So if we have CH3, CH double bond, CH, CH2, CH3, like this kind of an hydrocarbon, we will call it what? Pent. We will number it from here 3, 4, 5, because this double bond is being taken in the as a functional group, so it is always represented in the form of a primary suffix, and we need to indicate its carbon number on which it exists, so it will be pent to ene. Even if we have suppose double bond from here, let me give you the example. Let it be like this. Suppose from here, in this particular example, we are having double bond from here at carbon number 2 and we have a methyl group from here at carbon number 2. We will give preference to always a double bond. We will start our numbering from this side and we will name this compound as 4-methyl pent 2-ene. So it's like this. These double bonds can also exist in cyclic compounds, in alicyclic groups, and it can be like this. So if we have this one, this will be cyclohexene, and if suppose we have a double bond along with the 2-methyl, obviously we will start the numbering from which side? We'll start the numbering not from the methyl side, we will start the numbering from the carbon having double bonds. They must be given the lowest number, so it will be 3,3-dimethyl cyclohex 1-ene. So this is how we name the alkenes. Now let us see the isomerism in alkenes. Let us first talk about their structural isomerism. Yes, they show both chain and position isomerism. Let me show it to you. If we have suppose CH3, CH2, CH2, CH double bond, CH2, this is what we have is pent 1-ene. We can also have CH3, CH, CH3, CH double bond, CH2. Here we have 3-methyl but 1-ene. So see, the position of the double bond hasn't been changed. It's still on carbon number 1. But the chain earlier is of 5 carbon, now it's of 4 carbon. So that's why it's an example of chain isomerism. Whereas if we draw the same molecular compound with the same molecular formula like this, in this way, this is now is 2-methyl butene. So what we find is this is the position isomer of this one as well as of this one. So they both are position isomers, but this one this one is position isomers to both of these compounds. The reason being because the position of the double bond has been changed. Now it is at carbon number 2. That's most important. So it shows chain as well as position isomerism. Along with this, it also shows stereoisomerism. Very specifically, rather we can say in stereoisomerism, it shows geometrical isomerism. What is this geometrical one is? You need to know this. Due to the presence of the pi bond or due to this double bond character, the rotation along carbon-carbon bond becomes what? Impossible. That's not possible. So the position of the two substitution groups which these two carbons which are having a double bond can have, those positions becomes what? Fixed. And as a result, we can get two different spatial arrangements. Let me give you an example. Like if suppose we have, these are the four substitutions we can have on a double bond. Now if we have a group A here and a B here, A here and a B here, we can also have a molecule with the almost the same formula but this kind of an arrangement. What is the differences? Here the similar groups are on the same side and here they are on the opposite side. That makes them what? Different. Now when the same groups are on the same side, it's called cis isomer, and when they are on the opposite side, it's called trans isomer. And what we find is any alkene where the alkenes show this kind of isomerism and they differ in their physical as well as chemical properties also. Let me give an example. Suppose we have CH3C Cl double bond C, it can be ClCH3. So in this case what we find is the similar groups are on the opposite side, so it's a trans isomer, whereas if they are on the same side, what we find is they are called cis isomer. Now how they differ, these cis and trans is, let me explain it to you. Now these cis and trans isomers differs in their, not only in their melting points but also in their boiling points. Let me explain it to you. First, the melting point, what we can make out from this bond line representation, that always these trans, this will be the trans isomer, butene. So this trans butene is found to be having a more compact packing in the solid state because it is having the least steric hindrance. Whereas if we are trying to pack this cis one, this is for trans and this is for cis, their methyl groups are on the same side, we can't pack them very compactly. The reason being we get steric repulsions. As a result, melting point of trans isomers are always more than cis. Another important thing we can take the example is that if we have, suppose, now let us talk about boiling point and dipole moment. If suppose I am having this butene trans and I am also having this one cis and trans, what I find is this carbon is more electronegative than this one, so dipole moment is along this side, dipole moment is along this side, so the net dipole moment resultant is on this side. Whereas in this case it is on this side, it is on this side, so what happens is net dipole moment is 0. As a result, what we find is trans isomers are having least dipole moment or 0 dipole moment, so the intermolecular forces of attraction in the trans will be less. As a result, the boiling point of the cis will be more than the trans ones. That is how they differ from each other. Let us see the preparations of alkenes. The first method is from alkynes. This is by partial reduction. Why partial reduction? Because we only want to reduce only another pi bonds, and we want to retain one pi bond so that alkenes are formed and not alkanes. And now this is done by taking, let me give you the example. If suppose we have this is but2ine, and if we reduce it by taking hydrogen in the presence of palladium and coke, just partially poisoned or partially deactivated by using the poisons like sulfur and quinoline or xylene, what happens is what we get is this alkene. So we get cis but2ene. Now this palladized carbon or palladium with carbon which is being deactivated by using sulfur is called Lindlar's catalysts. So always remember, Lindlar's catalyst gives us cis-butene, whereas once the same reaction is being carried out by using sodium and liquid ammonia, both of these reacts to form sodamide and hydrogen is being released, what we get is the partial reduction takes place and we get trans-but2ene. So remember, and this is called Birch reduction, BIRCH, Birch reduction. So Lindlar's reduction, which is a partial reduction of alkynes, gives us cis-alkene. Birch reduction, which is using by sodium liquid ammonia, or the alkynes on this partial reduction gives us the trans-butene. That's the most important thing to note. And yes, of course, if we have any simple alkyne like this one, then in this case there will be no issues as such of whether it is cis or trans, because we can't get any type of geometrical isomers in this. So it will be a very simple propene in this case. So this is one of the methods of preparing alkenes. The next method to prepare alkenes is from alkyl halides. From alkyl halides we can prepare alkenes by dehydro halogenation. By dehydro halogenation, which is also called beta elimination. Now in this, what happens is, when any alkyl halide is being treated with alcoholic KOH, alcoholic KOH is KOH taken in ethanol. So that becomes potassium ethoxide as the main reagent. What happens is halogen gets removed, and along with this, hydrogen from one of the beta carbons is also removed. Now hydrogen from that beta carbon will be removed. Remember, that will be the major product, which is going to give us more substituted alkene, because that by more number of hyperconjugating structures will be more stable. That's why the hydrogen is always being removed in preference from the carbon atom, which is going to give us more substituted alkene. So definitely this is the one which is going to be giving us more substituted alkene. So one hydrogen from this carbon and this bromine is being lost, and what we get is this alkene as a result, which is but2ene as a major product. We also get but1ene, of course, but that will be in a small amount. So the major product will be this, along with a very small amount of this is but1ene. So that's the most important thing to note in this, that this is how the dehydrohalogenation takes place. The reactivity of alkyl halides is in this order towards this reaction, that iodides, bromides and chlorides are the ones. This is how they react. So the most reactive are in this case the iodides. And if we have a degree, remember as per the degree is concerned, the degree will be in the order tertiary will be most reactive, followed by secondary and primary, because tertiary gives us what the tertiary carbocation, and the tertiary carbocation very easily in the basic medium gives us what alkene. Elimination reaction is preferred in this case, not a substitution reaction. We can also prepare alkenes in the next method by heating vicinal dihalides with zinc. Vicinal dihalides are the ones which are having two halogens on the neighboring carbon atom. So when such alkyl halides, like if we have like this one, this is called 1,2-dichloropropane. When this is heated with zinc, what we get is CH3CH double bond CH2 plus ZnCl2. So this is how we can prepare alkenes by this reaction also. The next method of preparing alkenes is from alcohols. From alcohols we can prepare by acidic dehydration. Of course, we are taking out water from an alcohol so that alkene is being formed, so the process is called dehydration. But what is being done in this case is, like this is the alcohol, it is actually being taken with sulfuric acid at a higher temperature, higher than 170 degrees Celsius. That's why it's called acidic dehydration, where this hydrogen from this one sulfuric acids attacks on this OH, makes it an oxonium ion, which leads to what? Its elimination, giving us what? CH2 double bond CH2 plus water. So any alcohol on acidic dehydration gives alkene. Now let us see the properties of alkenes, and we will see first the physical properties. In the list of physical properties, we know that almost their properties are very similar to one of the alkanes. Let us first discuss their state. Yes, C2 because C2 to C4, they all are your gases. Then C5 to C18, they are liquids, and C19 or above are solids. So that's the basic thing about them, that they just state. Then their melting point and boiling point follows a very similar trend what we have seen in case of alkanes. It increases with the increase in the number of carbon atoms, and as such they doesn't show much variation. And only difference is that we know I have already discussed that how their melting points and boiling point differs due to their geometrical isomerism between cis and trans, and because of their dipole movement. Then we have solubility. Yes, as such very similar to alkanes. They are insoluble in polar medium like water, and they are soluble in non-polar organic mediums, organic solvents like benzene, CCl4, etc. Then let us see their chemical properties. And the first reaction in the chemical properties is called hydrogenation. Yes, we can anhydrogen. This reaction we have done in the first in alkanes as the preparation method. We know that if we take any alkene, we can hydrogenate it by heating it in presence of platinum or palladium or nickel, and it will give us what? An alkane. So it always gives us an alkane on hydrogenation. And this process of adding hydrogen to any unsaturated one alkenes or any alkyne is called hydrogenation. The second reaction is the addition of halogens. Addition of halogens. Remember, addition reactions are their major reactions because, of course, due to that unsaturation, we can always add something to these molecular species, and that is why their addition reactions are the main characteristic reactions. And that too, electrophilic addition reactions because of the high electron density of the double bond pi bonds, pi electrons. Addition of halogens in this, what we find is if to any alkene, like if we take bromine in CCl4, of course, what happens is bromine gets added to both the sides across the double bond like this. So what we get in this case is your vicinal dibromide. So it's 1,2-dibromopropane we get. Similarly, we can add chlorine. We get this vicinal dichloro product. But remember, in case of bromine, since bromine in CCl4 is orange red in color, the moment it gets added to any of the unsaturated compounds like alkenes or alkynes, its addition takes place across multiple double bond. Then what happens is the brown color, orange red color of the bromine gets discharged, and that's an indication or a test to check the presence of unsaturation in any organic compound. The next reaction of alkenes is the addition of halogen acids, the HX. Now let us take an example of the addition of any of the halogen acid in an unsymmetrical alkene. Let us take if we are adding HCl. Now the HCl in this, we have of course H plus and Cl minus. One is an electrophile, other is a nucleophile, and they can go to any of the carbon atoms because it's an unsymmetrical alkene, symmetrical alkene. So this will give us the product like this one. So what we get is we get alkyl halides as the product on addition of halogen acids to alkenes, and we get in this case this is called ethyl chloride. But remember, whenever the addition takes place to unsymmetrical alkenes, follow Markovnikov's rule. What is this Markovnikov's rule is? It was a Russian scientist who actually cleared us, who gave us the concept that during the addition of any other molecular species to unsymmetrical alkene, the negative part always goes to that carbon atom which is having what lesser number of hydrogen atoms or which is more substituted. And the basic idea behind this rule is that actually the molecular system follows the formation of a more stable carbocation. Let me explain it to you with an example. If suppose we have this propene, this is an unsymmetrical alkene, and if we are adding HCl to this, definitely the negative part of this molecular species, the Cl, as per this rule, will go to that carbon atom which is having lesser number of hydrogens. So out of these two, it will go to this carbon, and this carbon, or which is more substituted in fact also. So what we get as a product is this isopropyl chloride and not N-propyl chloride. So this is what we get, or we get 2-chloropropane. Now let me explain it to you that the mechanism behind this reaction. The mechanism says this HCl in the first step breaks down into to H plus and Cl minus. Then what happens is the addition of this electrophile on this alkene takes place. Now due to this what happens is electromeric effect works. Shifting of the pi bond will take place to any one of the carbon atoms, and this can shift to this carbon number first, and this can shift to even second carbon. But it will shift to only to those carbon definitely which will be resulting in the formation of a more stable carbocation. So this will not take place, and once this pi bond gets shifted to carbon number 1, it attracts this H plus, and this gives us what? HCH-CH3. Now by this we have got secondary carbocation, 2-degree carbocation, which is much more stable. Then what? If this could have happened, this could have given us this kind of a carbocation, which would have been a primary carbocation, which is not that stable as the secondary one is. So of course the molecular system prefers to go to what intermediate, which is more stable, secondary carbocation. And once this secondary carbocation is being formed like this one, now the addition of the Cl minus nucleophile takes place on this, and this results in the formation of this product. So this is what is the basic of the Markovnikov's rule is, that it involves the formation of a more stable carbocation. And let me explain it to you with other example also. If suppose we have this alkene and we have HBr, of course what will happen is the Br will go to that carbon atom negative part which is more substituted, this one, and in this case what we get is BrCH3, CH2, CH3. This is what we get. But we have a very much opposite effect of the Markovnikov's rule, which is called anti-Markovnikov's rule also. Anti-Markovnikov's rule, which is also called peroxide effect. It is only applicable for HBr in presence of peroxide. So what does this effect is? If to an unsymmetrical alkene HBr is added in presence of peroxides, the reaction follows not the electrophilic addition reaction mechanism, but it follows a free radical addition reaction mechanism, and in this the bromine goes to that carbon atom which is actually is least substituted or which is having more number of hydrogen atoms. So in place of going bromine into this will go to this first carbon atom, and the product obtained will be your this. Remember, this is called anti-Marconi-Curves rule or peroxide effect, and it is only applicable for HBr because HF-HCl's bond enthalpies are very high. They never gives us free radical, and iodine free radical formed is unstable, and even its addition to the alkene is an endothermic process. So endothermic step, that is why this particular addition is only, or the mechanism is only applicable to HBr. Now peroxide makes this reaction to go in a free radical mechanism manner. Let me explain to you the mechanism of this reaction. Now let us see the mechanism of the anti-Marconi-Curves rule. In this, what happens is, firstly the benzoyl peroxide, which is being used as a initiator under the influence of the UV light or the high sunlight or powerful sunlight, broken down into what the benzoyl, this is carboxylate free radical. This carboxylate free radical then changes into phenyl radical plus CO2. This phenyl radical combines with HBr and it leads to its homolytic fusion, which gives benzene and bromine radical. Now this bromine radical shows what a free radical addition to this alkene. Now due to which what happens is free radical homolytic for homolytic fusion of the pi bond of the alkene takes place, and this bromine can add to any one of these, if it to a carbon number 1 also and carbon number 2. If it adds to carbon number 1, that will be an option number 1, and if it adds to carbon number 2, that will be an option number B. Now in this option A takes place, what we get is we get a secondary free radical, and if the bromine goes to second carbon, remember the free radical we get is this one, primary. Of course, which is more stable free radical is the secondary one. That's why this doesn't form, and this is formed. Primary is not formed, secondary free radical is formed, and as a result this secondary radical formed CH3CH2Br again combines with one more HBr molecule, and it takes out hydrogen from here, and this results in the formation of this N-propyl bromide plus bromine radical, which again shows the similar chain propagation steps, and this is how we get bromine added to the any of the unsymmetrical alkenes, and the bromine goes to the lesser substituted carbon atom. Now let us see the addition of cold sulfuric acid, concentrated sulfuric acid, to any of the unsaturated, unsymmetrical, this is cold and concentrated sulfuric acid. So let me explain to you. Whenever the sulfuric acid, cold and concentrated sulfuric acid is added to unsymmetrical alkenes, addition takes place as per Marconi-Curves rule. We know that it breaks down into H plus and HSO4 minus ion. So what we get is CH3CHOSO3H and CH3. So the product formed is called alkyl. Let me tell you, in this case it is isopropyl hydrogen sulfate. So this is the hydrogen, this is the sulfate, and this is the alkyl part. And so what we get on addition of the cold and concentrated sulfuric acid to unsymmetrical alkene, which follows Marconi-Curves rule, we get alkyl hydrogen sulfates as the product. Now let us see the next reaction, which is the addition of water, called hydration. The addition of water takes place, of course, in acidic medium, because we need to have a proton or H plus or an electrophile, and it follows Marconi-Curves rule. So if we have CH3C like in this way, we have 2-methyl propene, and water is being added in presence of an H plus. What we get is definitely this carbon will acquire, more substituted one will acquire the OH, and we get tert butyl alcohol as the product. So this follows, yes, Marconi-Curves rule. Let us see the next reaction of alkenes, which is called oxidation reaction. In this, what happens is addition of KMNO4 is done Now when any alkene is subjected to what let us take first cold dilute KMnO4. We can also have alkaline KMnO4, which is called Bayer's reagent. Now this Bayer's reagent basically does the work of hydroxylation. It adds what 2 OH group across the double bond, and that is why we call it a hydroxylating agent. Now let us see how this reaction takes place. So when this is reacted with dilute KMnO4 or alkaline KMnO4, the product obtained is OH and CH2OH. So what we get is propane 1,2-diol. If we take ethene in this, remember the product obtained in this is glycol. So very interesting product, and this is what is oxidation is, addition of oxidants is taking place. Now, how it becomes different is we need to realize this. The moment we take, let's take the second part. The moment we take acidic KMnO4, or we take the simple KMnO4 on heating also, or we have whatever the taken KMnO4 we have taken plus heat, even then also what happens is the breaking of the alkene takes place from the double bond position, and this results in the formation of what either an aldehyde, most probably the ketone is formed and the carboxylic acid is formed. So a ketone, carboxylic acids are formed. Let me give you an example. Like this alkene is subjected to what acidified KMnO4. Its breaking takes place. The C will form a double bond with the oxygen, so this part will give us what a ketone like this, propanol, and this one carbon gets oxidized further to what, formic acid. So these are the product obtained when we react this with acidified KMnO4. Let me give you one more example. If suppose we are having butene on reaction with acidified KMnO4 results in the breaking of this molecule from the position of the double bond, and what we get is the acid of the corresponding parts. Since it was a symmetrical alkene, we get 2 molecules of acetic acid. Also need to remember the permanganate color of KMnO4 gets what, decolorized, so that's why the decolorization of the KMnO4 is again an indication of the presence of a unsaturation or a double bond in the organic compound, and it is one of the tests to distinguish between saturated and unsaturated, or an alkane and alkene. The next reaction of alkenes is again very important, which is called ozonolysis. There is a reaction of alkene with ozone which results in the formation of ozonide, which on reaction with zinc water reductive hydrolysis which gives us mainly the aldehydes and the ketones. Let me explain it to you with an example. Like if suppose we have this alkene, when this is reacted with ozone, this attacks the double bond, the carbon organic compound from the double bond position, and this forms this compound, which is actually called ozonide. Now this ozonide on reaction with zinc water leads to what, the cleavage of the compound like this. This gives us what, CH3CHO, and this gives us what, along with this oxygen, it gives us what, the HCHO, and these are the 2 products we get. So this reaction again is used to detect the location or the position of the double bond in the long chain hydrocarbons. That was the main purpose of doing the ozonolysis, because it breaks the alkene into 2 parts from the position of the double bond. And what we get accordingly, aldehyde or a ketone, if that carbon which was having a double bond is having only one alkyl substitution, we get aldehyde. If no substitution, we get formaldehyde, and there will be, if there will be two substitutions, we'll be getting ketone. Let me give you another example of this. Let us suppose we have CH3, CH2, CH, CH3, double bond. This will not be having any double bond. This one, CH, CH, 3. So this on ozonolysis will give us what? CH3, CH. Let me start from here. CH3, CH2, CH3, CH3. This on reaction with zinc water leads to breaking of the bond like this. What we get is, we get a ketone of this one. This oxygen goes with this chain. So it is CH3, CH2, C double bond O, CH3, and we get this also plus CH3, CHO. So these are the two products obtained on ozonolysis, and this is how we get different products from the ozonolysis of alkenes. The next category of reactions of alkenes are polymerization reactions. In this, smaller units of the alkenes combines with each other under the influence of a high temperature, pressure and catalyst, and forms long chains of the repeating molecular species, and which are called polymers. The small repeating units are called monomers. Let me give you an example. The most common is this ethene molecule. This ethene molecule, under the influence of high temperature, pressure, catalyst, its N molecules combines to form what? Long chain of the CH2 species. This is called your monomer, and this is called polyethene. We call it normally polyethene or polyethylene, which is one which is actually being used to make number of products, not only which it is used in making your packaging materials, but it's a very common and most commonly used thermoplastic in our day-to-day life. We can also have this propene, which on polymerization and number of this results to what? The formation of polypropylene, which is again is a very important one of the thermoplastics we have. So alkenes basically undergoes polymerization under the extreme conditions, and yes, they form long chain compounds which are called polymers, and which are very, very useful in our day-to-day life.